Well, today is a pleasure to have Jordi Salvador. He will tell us about neutrino properties from cosmology, and I remind you that we will have a coffee break after 15 minutes, and the total duration of the talk it will be 30 minutes. In the coffee break is a 10-minute coffee break where you can ask questions or take a coffee or whatever you like to do. And I also would like to remind all people that well, this space is for postdocs and PhD students, and they are all kindly invited to propose talks. Anybody that can tell us something interesting about his own work, we have a lots of free slots until June. So please suggest names and volunteer for the next talks. So please, Jordi.
Okay, thank you very much. It's a pleasure to give this talk, and I hope you enjoy. Now, I work in neutrino physics and particle physics, astrophysics, and cosmology, also some dark matter. And for this talk, I choose the topic of studying properties of neutrinos by using cosmological data, which is, I think, a very interesting field and something I like quite a lot. And then I will tell you a bit more concrete, something the last paper I did with Ivan Esteban, but first I will give you an introduction of what is all this about. And this is a very propagandistic slide of what we know about particle physics, right? This is the content of particles that we know by experiments. And indeed, one of the most important experiments probably that gives us a lot of information about this setup of particles is high energy physics. Now, we know very well from colliders. I don't know if I can move this. Oh, wait. Yeah, this is better. We know very well from collider physics that by smashing particles, mainly this first family of particles, we end up creating a lot of other particles that we identify as the second and third family. And also we learn about new interactions. We learn about these heavy mediators that mediate the electroweak interactions. And we learn about gluons, and we already knew the photon. And mainly we discovered the Higgs recently, right? This is a very big discovery of high energy physics. And we didn't see the graviton yet in high energy physics, but something that some people is speculating about it, or maybe if gravity is not simple. And there are two main different particle contents. One are the quarks that are interacting with the strong forces and electroweak forces, also electric and weak forces, and then the leptons, right? In these leptons, we have this, the one that we know very well, the electron. We have the partners of the electron, second and third family, the muon and the tau, that are heavier. And we have the very funny ones that are the neutrinos. Neutrinos are very interesting because the last decades we discovered that these particles have indeed tiny masses, and the difference between the masses of the different mass eigenstates that is not aligned with the flavor eigenstates produce what is called neutrino oscillation physics. Now, this is a field that was very active with a lot of experiments and very interesting one. Now, the fact that they have mass is also interesting because we can test properties, or we can use even cosmology to tell something about that. Now, let me tell you, let me put this 1 second. Let me tell you a little bit how everything started somehow, this idea of looking for forces. And there is one very important first force that humans understood somehow, and it was done by Isaac Newton, as you know very well, and this is gravity. Newton did studied how the planets move and all this very macroscopic physics, and he understood that forces, because this geometrical interpretation of forces, they should indeed be something that acts at distance, and it goes as 1 over the distance squared of the different objects. Now, what is responsible of these forces is the amount of mass. If you are heavier, you produce more force, and if you are weaker, you produce less force. Then the force is something like this, when this g is a constant that we now call a Newton constant of gravity, right? This is a very important first force that we understood. A second one that it started with electromagnetism, and then later it bring a lot more physics. It was the This is an example of the electrostatic force that it was discovered it was proposed by Coulomb. I put a disclaimer here that I don't know if you can read, but indeed there was evidences for this kind of forces from a long time ago, because there was some people rubbing cuts in some materials and they produce electrostatic forces. And that was known, it was kind of a mystery probably. And then at some point, Coulomb, probably inspired by this idea, he proposed a 1/r² force. This is an example of the setup that he was using. Now, why these two forces were kind of the first that were discovered? The idea is that they use a lot of particles. They are forces that are long-range forces. They extend in macroscopical objects, and they can be enhanced by the idea that you extend the force in many, many particles. An example, if you take the mass of the Earth, you divide it by the mass of the protons, the gravitational force is adding up to 10 to the 51 particles, right? This is what makes it visible, even though it's the weakest force. And still at high energies in colliders, we don't have evidence for that. Similar numbers happens with the Coulomb, not so much, because electric interactions are much stronger, but there is still quite a large number of electrons in any macroscopical charged object that you can measure forces as Coulomb did with this torsion balance. Now, this is an interesting idea. The fact that you can use large number of particles, you can test forces that are very weak or pretty weak, right? And use large extensions of particles to test these fundamental forces. And this plot that you can see here is an example of what we are doing today with that idea, right? There are different experiments like Casimir experiments or torsion balance, or even the movement of planets, that are used with by using the same idea of that the force is weak, but also extends in very large number of particles. They use that to put constraints in the couplings. This is small, it's a bit too small, but this is around 10 to the minus 30 times electromagnetic coupling. This is 10 to the minus 40. And you can see indeed that by using planets or distortion balances today with very high precision, we can test also fifth forces. Now there is a caveat if we compare with the particle content that we know it exists, and is that all these tests indeed involve only particles of the first family. That's obvious because these other particles in the second and third family are unstable, meaning we cannot produce like a torsion balance made of charm quarks, right, or top and bottom quarks, or even muons or taus. This is very complicated to get macroscopical size objects with this second and third family, and at the same time, this means it's very hard to test these fifth forces, or these very weak long-range interacting forces. But the question is, can we really think some way of testing second and third family fifth forces? And there is an answer to that, and the answer is using neutrinos. And I told you these neutrinos have very tiny masses. They are very, very light. And the mass states are not aligned with the flavor states, meaning if you have a neutrino in a mass state, it's a certain combination of flavor states. It has pretty much the same amount, let's say, of electron, muon, or tau flavor. And we know very well that the neutrino background in the CMB is made of mass states, meaning we have really a background of a lot of neutrinos, hundreds of neutrinos per cubic centimeter, which are pretty much the same amount of electron, muon, and tau neutrinos. Then this is remarkable, and it's not something you can do with other families or other setups. And it's a good motivation a priori to study what's the effect of this physics in neutrinos, right? And especially using this cosmological neutrino background, which is a very interesting. It's a very interesting fact that we have all these many neutrinos in these funny combinations of flavors everywhere in the universe. And this motivates the use of cosmology. And the idea is that when this is today, right, this is a typical picture. You saw this picture 1,000 times. And this is the Big Bang here. Everything started with this instant. Then there is the inflation period where everything expands very fast. And then the reheating, everything becomes very high temperatures, and the universe starts cooling down and expanding. There are a couple of periods here that are interesting, and we have measurements somehow, data. We have something that tells us something about the physics that is happening around these times, and it's at BBN where the nucleus are produced. This is something that we can tell something about that by estimating or by measuring what will be the relic abundance of different elements, and the densities there can be of order of 10 to the 30 cubic centimeter, the number of particles per cubic centimeter, which is quite high. this is in comparison with what Newton was doing, right? The idea of like using a large number of particles and what's the physics, what the new physics, this long range physics may imply on that. And especially in the case I'm going to show you for neutrinos. Another period that is extremely important for cosmology is the CMB time, which happens here, where the universe become neutral. I mean, all the hydrogen atoms get electron, and the photons propagate free, and that's what we see as the CMB, right? Now, this is very interesting, but what we see on that, we have data, very precise data. We're in the era of precision cosmology. That's really amazing, and we can do a lot of things. And one which is probably the holy grail of cosmological data is CMB data. And today we have this Planck 2018. I show you here the picture of what Planck is seeing, but it sees a lot more than that. It sees we have all the information about all these multiples in the sky, but also we have polarization. We have a lot of other things like lensing, and it's very rich data set with a lot of information about cosmology. We also have the matter power spectrum. This is illustrated in this plot here. The matter power spectrum is referred to the Fourier transform of two-point correlation function of the distribution of matter later. This will be related with the galaxy distribution in the universe. And we also have we also have what we call the baryonic acoustic oscillation. That's the scale associated with this wiggling oscillation that you cannot see in this plot. And it's kind of a bump if you do the Fourier transform of this in the scales. It's the oscillation scale imprinted by baryons, by the baryonic acoustic oscillations in the large scale structure. It's also a very interesting scale that we can extract a lot of information about the expansion history of the universe. Now, how we parameterize cosmology or how we do cosmology, and this is again a kind of a cartoon slide, but pretty much to get familiar with some of the letters and numbers that will appear soon at some point. The universe is expanding. It goes from here to the right. And sometimes we use as parameterization for this expanding different letters. We use this expansion, this scale factor, which is telling us how the lengths change when the universe is expanding. We use also time, we use the redshift, and we use the proper time. Those are different ways of parameterizing that sometimes you will see expressions in cosmology expressed in one or the other. How the universe at every instant of time is expanding, how fast it's expanding, is determined by this parameter, this Hubble parameter, which is A dot over A. And the other thing we know, because that's something we know because of the data, I mean, we see the universe at very large scales, and we know the universe is pretty much homogeneous, and it has small perturbations on top. This small breaks through for smaller scales later. Here, for example, in the smaller scales, you have very high nonlinearities and everything becomes very complex. But as soon as you look at very, very large scales, you should be fine. Then for the purpose of this talk, I'm going to assume that we always look at linear cosmology in the sense that we solve these Einstein and Boltzmann equations for all the components in the universe in using linear physics, if you want. The perturbations are always very small, and the universe is very well approximated by homogeneous and isotropic solution. Then there are tools to solve this kind of Boltzmann plus Einstein equations. I put here an example by Les Gorges. This is very well-known code called class. That is the one at least I like to use because it's kind of a bit more modular in the way you can modify. And but that's the physical setup. We do physics in cosmology, like very briefly, right? Now, what do we have in the universe? What are the ingredients we have in the universe? And here you can see the different components we have. We have radiation today. It's nothing. It's just tiny amount of energy in the universe. Us, which is everything but hydrogen and helium. I mean, we have some hydrogen, but this is to illustrate what planets and all this are. It's about 0.025%. It's not so much. Neutrinos are about 0.5%, which is a bit more. This is the ones we are interested. And then we have other things like stars, all the hydrogen, and of course the big two unknowns that we don't know, the dark matter and the dark energy. In this talk, because of the title mainly, we're going to focus on studying properties of these guys, of these neutrinos. Now, let me tell you very schematically what happens with neutrinos, right? Neutrinos are particles that are very light. They are supposed to be very light. And then in the history of the universe, they cool down and they become non-relativistic at some point. Now, this is an illustration of what's the energy of the universe. You want temperature, momentum of particles, whatever you want. And we will draw here a neutrino distribution function, right? That they have a mass. And then the distribution function will go from high energies to low energies like this, right? It happens slower, but this is pretty much the idea. Now, what happens here is that indeed neutrinos go from going very relativistic, and this happens maybe before recombination. I mean, it's around that time, depending on the mass you put, to become non-relativistic. And all this happens at CMB or maybe later, depending on where you put this mass, right? Notice that if I move this mass to the left, this step function will move to the left. And if this should be centered here always, right? Put it to the right and it moves to the right. This function here is the plot of the equation of a state for this fluid of neutrinos. Neutrinos is a fluid that fills the universe, and it has an equation of a state that tells us how the energy of the system changes when you change the volume, or if you want the relation between pressure and density. Now, when particles are relativistic, the density is always 1/3. And this is the regime we are here, where all the neutrinos have momentum or energy higher than the mass, while they cross this region. This is a very interesting phenomenon that happens, and then all they are here, meaning they become essentially like dust at the level of the equation of a state of the universe. Now, what can we use this setup to test particle physics? Can we go beyond this idea of like having neutrinos that don't interact at all and they just become non-relativistic to test other properties of neutrinos? And the answer is yes.
Jordi,
dime.
Maybe we can make a break here, no?
Yeah, that's fine. That's fine.
Okay, yeah. I'm sure there are questions.
Very good. Can you
go to the previous slide?
Yes, the one that is moving, no? This one.
Yeah.
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 Tell me.
Questions?
Oh, sorry. This is moving. So. I mean, it's all very schematic, but
I don't understand. How do you go from omega equals 0 to omega equal 1/3? What is in this axis?
This is this is the same axis. This is energy. If you want the energy of the fluid, right? You have all these neutrinos that they have some temperature or mean momentum of the particles. And when all these particles are relativistic, the equation of a state of the fluid is telling you how is the ratio between density and pressure, right? And when you have a relativistic fluid, this equation of a state is 1/3.
Yeah.
When all these neutrinos are here in this on the right of the mass, essentially they behave like radiation, like photons, right? When they cross this line and they become non-relativistic, they behave like dust, meaning the pressure doesn't play any role. The energy just gets redshifted like a to the cube, right? There is no pressure. Pressure is 0 in this side. Then it just happens that you go from here to here. You have to think that this distribution is not anymore in any thermal equilibrium. It's a Fermi.
In the cosmological setting, is there any relevant period where neutrinos are non-relativistic?
Yeah. Today, neutrinos are non-relativistic. At least we have neutrino oscillations, right? And there is two mass splittings that both are larger than the temperature of the neutrino background. Meaning, if the lightest of the mass is maybe relativistic, of course, the other two, they should be not relativistic today. That's why neutrinos and masses of neutrinos is very interesting in cosmology, because late cosmology, I mean, large scale structure and even CMB physics is sensitive to this, right? And we know that it should be something you should be able to see. So yeah.
Oh, somebody else was me? Okay. I don't know if somebody else was trying to ask.
No.
Maybe me? Can I ask?
Yeah, sure. Everyone.
Yeah, so maybe this question is silly, but why do they become non-relativistic if they decouple early?
Okay, the idea is that we know the physics that makes them decoupled, right? We know that neutrinos interact during BBN, electron neutrinos interact during BBN, and we know how they interact a bit earlier than that. Now, because we know the electroweak physics. Now, if you know the electroweak physics, you know when neutrinos will decouple, and you can give them a temperature, right? And this happens pretty late. It happens maybe during BBN. There is no any entropy dilution, or at least big entropy dilution like UCD or anything. Now, that tells you the temperature, right? That tells you the temperature, which is similar to the SIMB temperature, and then you just redshift it as a normal fluid until you reach the mass, and then they become non-relativistic, right? The kinetic energy of the neutrinos, they keep decreasing with expansion of the universe. I don't know if that answers the question. But we know the physics of the moment they decouple, then we know the temperature pretty well.
So Jordi, I also wanted to ask, you started the talk mentioning these very interesting limits on any possible fifth force or some other interaction. And then basically, so now you're going through all these components. So you're trying to see if there are ways to put limits on any possible other interaction, for example, with these neutrinos or some other kind of particles, right?
Exactly, yeah. In a moment, I will add an interaction. I'll tell you a bit the phenomenology of that in this setup of neutrinos in cosmology.
Yes.
That's the idea. The idea is that, I mean, it's funny, right? Because it's the only setup where you really have these high densities. I mean, these long-range interactions, very weak interacting long-range physics, it's very hard to test. And for neutrinos, it's even harder because neutrino experiments, they don't have, in particle physics experiments, they don't test very well this physics. Cosmology can do that. That's remarkable, in my opinion.
So one other interesting thing is you mentioned the percentages of all these components, like planets, stars, and so on, right? And another one is black holes, like the black holes that LIGO is detecting. So then, we know that stars are making black holes. So the kind of black holes of stellar masses, most stellar evolution models would predict that their contribution to omega today is at least 10 to minus 4, or maybe even a few times 10 to minus 4. And then, of course, there's also the very massive nuclear black holes. These are a little bit less, the contribution to omega. But so is it possible also that there is any other kind of interaction these black holes might produce that would change something?
That's interesting, but maybe, I mean, depends, right? The thing there is people studying long-range, massless long-range interactions, right? Like modified gravity physics. And that's widely studied, something that affects cosmology, and it will affect large scale structure, the growth of large scale structure at linear order too, and it eventually will affect also planetary or black hole physics or a lot of other things. That's something that can be tested. What I'm going to focus here is more in the intermediate range. I mean, short range, but not cosmological range. Something like maybe solar system, a bit larger than that. But of course, if this is something in the black holes that affects also this physics, you should be able to if there is something like this, some new physics in the black holes that it's mediating interactions at some relatively short range. Probably these curves that we fit with LISA and LIGO, they will be different, right? I mean, they will start accelerating in a funny way, I guess, at some point. But it's something that, you can test that, I guess. You can use black hole merging to test modifications of gravity. That's probably, that's an interesting, probably it's already some people thinking on that. I mean, it's a very interesting question. I don't know if that answers, I mean.
Yes, thank you, Jordi.
No, you're welcome.
So what is the present bounds on the neutrino contribution to dark matter?
Neutrinos, they as we understand everything, they should not be dark matter because they are relativistic until very late.
Yeah, but there are bounds, no?
Yeah, but there is one very strong bound that comes from Catherine, right? Catherine already tell you neutrino masses should be less than, I don't remember the number now, maybe 3 electron volts or something like that. Meaning it doesn't work with dark matter, right? I mean, it has to be a very small component of the dark matter content. It's something related with this number, probably.
Negligible component.
Yeah, that's what you expect, I guess, something like that. You see, this number is much larger than this one, and this is because they have mass, right? I mean, if they were massless, they will keep redshifting as radiation, and they will get much more diluted today. Mm-hmm. But since they have mass, they store more energy. When they become non-relativistic, they dilute less, right? They dilute like a to the cube instead of a to the minus 3 instead of a to the minus 4. Then it's much less than this.
Right.
But that's assuming all the standard model physics, right? There is a lot of assumptions.
Yes. Yeah. Okay, I think we can resume with your seminar.
Very good. Thank you for the questions. And let me tell you 1 second, right? Why CMB is sensitive to that, for example, and which is also a very cartoonish way of telling that, but it should be fine. I mean, CMB physics is measuring very well this scale. This is the peak, the position of the peak, if you want, measured in the angular distance in the sky that you see. And it has 2 factors here. It has a factor that involves the integral from the recombination time to infinite, meaning this side here. This is related with this, and it has another factor that integrates from today to the recombination time, which is this side here. Now, as you can see, the recombination time is driven by atomic physics. We know how electrons get into nucleus. And if I move this mass from this side to this side, since this affects how energy density scales, and energy density enters directly in the Hubble parameter, these integrals that involve the Hubble parameter will have something to tell in this picture, right? Through all this correlation. Now, CMB is very sensitive. This is relatively a propaganda because there is a lot more physics. This is very well measured, and then you have to look at what will be the effects on this. But it's a priori very sensitive to physics that involve from today to the recombination time, and from the recombination time to the infinite past, if you want. But at least all the time that sound can propagate in this primordial fluid of baryons. Very good. That's very interesting. But now let me go in how we can extend that and what we can test, what properties of particle physics or other physics we can test with neutrinos in cosmology. Now, this is the Boltzmann equation for the propagation of the fluid in cosmology, right? It has 2 sides. One is the left-hand side, this capital D. It contains everything that involves gravity. For example, it will contain the covariant derivatives once you put the spatial derivatives and momentum derivatives, and it contains the effects of gravitational fields. And a lot of people that is studying modified gravity also add like massless long-range interactions, and they study how massless long-range interactions affect the growth of a structure and the propagation of these Boltzmann equations. I told you there are tools that solve this in a very, very precise way at the linear order. That's where we are working now, right? Another possibility, if you're a particle physicist, you will like a lot this side here, because here you put in a scattering interaction. Scattering interaction is something that interchanges momentums between particles, and it creates and destroys particles. And this is very particle physics way of testing neutrino physics. Now, this is a list of references that you don't have to read because probably you cannot, but there is a lot of people working on this and a lot of people working on this. Now, this physics involves scales of 10 to the 34 electron volt to the minus 1, more or less, which is around the size of the horizon. It's like scales of massless physics, very long-range interactions. It can be less than that, but at least it should be something that involves cosmological scales, lengths of interactions. On the other hand, these people here, they're working very short-range interactions. Those are scatterings of pairs of particles, and everything should be encoded when they are very close. Now, there are a few orders of magnitude between this, and this is something that we were puzzled for a while, and like what happens if you add physics there, and that's the question. It's the question we asked, right? Can we explore physics in this intermediate range, where indeed is long-range field forces, but much larger than point-like interactions and much smaller than any cosmological scale, right? We can indeed neglect this physics in some regime in the middle, and you can see there is room. It looks like there is a lot of room where you can neglect both. And this is something we work with Ivan. Here is the guy, Ivan Esteban. And this is the paper you can see. And I'm going to illustrate a little bit what's the results we found and why I think it's interesting also the interplay of this physics with neutrino masses in cosmology. Now, the idea is the following. Here is the picture of what we have, and those purple dots are neutrinos, right? And we add an extra interaction. We add a scalar field that mediates an interaction between neutrinos. This scalar field is coupled with neutrinos with this coupling, G, and these neutrinos have this mass M0 that now we know it should be, let's say, less than 1 electron volt because Catherine is telling that. This scalar field has a mass, and this mass is telling how long will be, what's the range of this interaction. This distance here is 1 over the mass, right? Now we expect something non-trivial a priori, right? The universe is getting denser and denser, and you expect some physics that is non-trivial when these particles get close together, right? You start having finite size effects that may involve more than 2 particles, may involve 3, 4, or a lot of particles. And eventually you may have an enhancement of this large number of particles. Now, I'm going to go pretty fast here. It's just to illustrate a little bit. But if you write the equations of motion of this physics here, you will have something that looks like the Dirac equation for a fermion, right? The Dirac equation is the equation that tells you how fermions evolve. And as you can see, this is just to illustrate this part. This will be the mass term of the fermion. The mass term has a correction that depends on this scalar field. And this looks like this. This looks like an effective mass, right? This is telling us that if you are in a very dense region, you should expect some corrections into the mass of this fermion. We also have the Klein-Gordon equation, and we take the approximation, which is very good in this intermediate regime, where the field is essentially following the fermions. We only have into account the field that is sourced by these fermions, right? This is telling us that the solution will look something like this. Now, how you go from here to here, you can look at the paper, and there is a lot of details on how you do the bracket of these operators with the thermal states and all that, and you reach this distribution. And you can see also that this distribution keeps holding, it's consistent with the fact that you add this physics. I mean, the physics is not...
Jordi,
sí.
What is the order of magnitude of the scalar mass?
The scalar mass is ordered, let's say, let me see if I have it somewhere here. It has to be, the range of the interaction has to be, let's say, maybe the solar system size, maybe a bit less, but not much less than that. And this is, what is that? 10 to the...
So it's very light scalar.
It's very light scalar, yeah, because if you add, I mean, if the scalar is heavier, I mean, what makes the scalar, the reason we need the scalar to be very light is the fact that neutrinos are very light, right? If neutrinos are light, you need the mass to be smaller than the mass of the neutrinos to get these effects, because this turns on when neutrinos become non-relativistic.
Aren't these scalars ruled out precisely by the fourth experiment that you mentioned at the beginning?
No, because these couples, these may couple second and third families and neutrinos, right?
But they couple to gravity as well, no? They will mediate gravity or not?
These scalars, I mean, they should not mediate gravity, no? I mean, they just couple I mean, in this model, we just couple them with the neutrinos, right? I don't know if it has to be, I don't understand, I guess, the question. What do you mean they mediate gravity?
Well, why we don't see these scalars to start with?
I mean, these scalars, we don't see them because they couple only to let's say they couple to the second family, right? Then we won't see them. Or they couple only neutrinos. Imagine they are, for example, mediated by a sterile neutrino that is a bit heavy, and they couple to the active neutrinos by mixing, like some seesaw-like model. Then you should not see that in the electrons or up and down quarks.
They couple to gravity as well, no? The question is whether this couple to gravity.
They couple to gravity like
a phenomenological consequence.
Yeah, that's true. They couple to gravity. I mean, they couple to gravity in the sense that they contribute to gravity, right? I mean, they contribute to if every one of these neutrinos has this scalar field, gravity will see all this as something, and it will interact with all that. That's true, but that's not excluded. I mean, that's what we are going to do here. We are going to couple all these systems to gravity, right? Okay. And we're going to put bounds to that.
Okay.
Using cosmology. Of course, then you may tell me maybe some like structure formation in galaxies at this intermediate scale may affect something. That's a good place to study this new physics. But there are not many bounds because neutrinos are also very tiny portion of the total matter. I'm pretty sure if you do the same with dark matter, you will have stronger bounds on that, like galactic formation physics or something. But it's a good question. Anyway, if it's okay, I can now. Yes. Okay, we have this effective mass for the fermion, right? That it gets modified by this. And the other thing we see here is that if particles are relativistic, this momentum is very high. This kills this factor here, and the scalar field gets much less source by this physics. Then when particles are relativistic, essentially they don't, particles, neutrinos in this case, they won't source scalar field. That's the two messages of this slide. I will skip anything at first order because it's too complicated and doesn't bring much.
Sorry, so you're thinking of a high redshift situation where neutrinos are relativistic?
I'm thinking about the transition, right? I'm thinking about the early universe where neutrinos are relativistic. It will be this picture here, where temperature is very high and you have this suppression for relativistic neutrinos in the sourcing of the scalar field. Now the transition where they start becoming non-relativistic, it will get a picture like this, where they start becoming non-relativistic, start sourcing a scalar field, this becomes not so suppressing, and you have this enhancement of high number of particles, and then they get very diluted, much more diluted than the interaction length, right? This 1/m phi, and you get this regime where particles are. Essentially, you will have a correction on the mass, right? I mean, this object will gravitate a bit more because it has a scalar field, but it's not, you don't see any effect of the interaction between them. I don't know if that answers the question.
Sorry, well, so what is the self-energy of the neutrino due to this dressing?
The self-energy, it's...
I mean, just classical self-energy. I mean, this will be surrounded by this cloud, right?
Yeah.
So how massive is this cloud compared to the bare mass of the neutrino?
I mean, it's less than the mass, but I don't remember. I mean, look, I can show you.
So parametrically, is it suppressed by something? Or?
It's suppressed by the coupling.
By the coupling G, no?
The coupling is small. The coupling has to be small.
Yeah.
That's the only thing.
Mm-hmm.
Yeah. It's, yeah. Then I have some plots showing the sum of the total energy of the system, which includes everything. Then you can see that indeed is not much, this correction. But yeah, the idea is that the coupling is doing that. I don't know how we're going with time, but here is again the same picture as before. Remember, I showed you here these neutrinos go from relativistic to non-relativistic, and they do this step that they kind of go this way. This is here in this orange dashed line, right? Now, if you add this new physics, if you add this phenomena, right, you will get something that looks like this. You will get this initial region where basically they behave like relativistic particles. There is nothing exotic. We get this region where you get the equation of state even for some values of this ratio, this G/m divided by C. This is large, but this can be very small. And indeed, it has to be very small because this has to be also small. And in this region, you get this effect, which the equation of state gets even negative values because it at some point is kind of dominated by the scalar field. And then they get diluted very much, and you get this regime again, right? Then this is a toy physics model that is long-range physics interactions that change very much the way neutrinos go from here to here, and it should have observational consequences, right? It's physics that a priori is not excluded by anything that we thought of, and it should have cosmological consequences. Now let me show you the cosmological consequences. That will be the end of the talk. I think it's pretty much fine.
Jordi?
Now what happened? Yeah, sorry.
So the scalar field is m square phi square?
What? Say it again.
Is that supposed to be a part of dark matter, or how does it, what's going to happen afterwards?
No, I mean, this is going to be part of neutrinos, right? If you see, look, I'm going to go beyond my talk and show you a plot. If you see, this is the total energy, right, of a scalar field plus fermions. Mm-hmm. And this line here will be the total energy of not having an interaction. And this is the total energy having this interaction. Now, as you can see, it does something funny, but it always comes back, right? To neutrinos. I mean, essentially, you want this line today to be where neutrinos are. And that's because, you know, neutrinos have these tiny masses because of neutrino oscillations and all this physics. Mm-hmm. But earlier in the universe, during this transition, they can do funny things. And the goal, I mean, we didn't pretend to make this model like something, like something that is essential. I mean, the goal was trying to prove that there is a range of physics with relatively long-range mediators that brings a phenomenology that is not yet studied a lot, right? I mean, something quite exotic somehow. And it does funny things. Now, let me show you some of the funny things that it does. Now, here is a fit of Planck data plus BAO, baryonic acoustic oscillations. And this is the gray exclusion. Well, the gray, what is in purple is the allowed region for cosmological data. Now, in this axis here, we have the sum of the neutrino masses, and we couple this scalar field to every one of the mass, to every one of the flavor identically. I mean, there is no exotic couplings or any model tuning here. And here is the G over the scalar field mass, right? Now you can see when you put this interaction a bit stronger, the neutrino mass bound becomes weaker and weaker at the level that even you don't have a bound in this range, right? You should choose a range because this can go much farther. In this region, neutrinos will be relativistic today. That means they will be massless effectively, and neutrino oscillation experiments, at least in this very simple setup, should not allow to be in this region. Now, this is pretty interesting. Here you can see the result with only Planck data, and you can see BAO is very important, precisely because BAO is testing physics at late times, right? With all these curves do these funny physics things. Another important result, at least for experimentalists in neutrino physics, is that Catherine, an experiment dedicated to measure the kinematic mass of the neutrinos, may see a value of the mass, right? If this is true, then you may say, oh, this new physics allows Catherine to see in the next run a mass of like maybe 1 electron volt, right? And it will be up here. And then cosmology, it's telling you that indeed you need some funny long-range new physics. Now the future is even funnier, even more promising than this. And this is what I'm going to show you now. These are two examples of forecasts for Euclid. And Euclid is claiming that they can measure neutrino masses essentially. They can put a bound that it will be stronger than the minimum value you expect by oscillation physics. And here is a plot of what happens if Euclid doesn't measure neutrino masses, measures something compatible with zero essentially. And as predicted, it excludes the oscillation physics, right? And this will be a tension, right? It will be something puzzling in cosmology, like why Euclid is measuring this, or is excluding what we apparently see in neutrino oscillations. Again, this may be explained by this physics, right? Some funny physics that may relax the cosmological bound, but at the same time be non-relativistic today, having neutrino masses. You will be something up here, right? You will predict a range of new physics. That is if Euclid produced this result, which will be kind of exotic physics. Another option is that Euclid produce a positive result. They measure the mass. And if they do that, they will see a range here in the masses. They measure the mass here. We put this value just to illustrate. And what will happen is that Euclid indeed cuts part of the parameter space, meaning Euclid is good in that sense. It will help us to test a region of a priori unknown parameter space in long-range interactions for neutrino physics, which is very cool, and it should happen soon. Now that's all. Here are some conclusions. I don't know who is the time because there were questions and all that. But the main claim I wanted to do is that cosmology is great to test particle physics, and we can exclude even part of the parameter space. Neutrinos are pretty exotic, and we don't even know the mass mechanism or what's the physics behind neutrino masses, and they are worth to study. With neutrinos, we can test these fifth forces in the three families, which is also something non-trivial, I think. And there is a very interesting interplay between new physics, cosmology, and the importance of having both, right? If you have these new physics scenarios, both are very justified. Particle physics experiments and cosmology, they can be complementary and bring us some light into this. I think it's a quite good interplay. Thank you very much. I don't know if I did right with the time.
Yes, very good. Okay, thank you, Jordi, for this. I think a very beautiful talk. It was really, really nice.
Thank you
Are
very
there
much.
more questions?
I have one. So Neutrino has been examined by others, right? Like ICCUB or solar neutrinos and so on.
Yeah.
And
yeah.
Does that have some impact for?
No, that's a very good question. Yeah, in the sun, there is bounds on. I mean, there is different things. There is something called non-standard neutrino interaction physics, right, which is widely explored in neutrino oscillations. But that is a physics that involves neutrino interacting with matter, with ordinary matter. This is different. This is self-interaction of neutrinos. Now there is bounds from solar neutrinos, because in the sun you produce a lot of neutrinos. You have regions that are very dense, especially inside, dense in number of neutrinos. I'm not thinking about ordinary matter. And you may put also bounds to this physics. They are relativistic, then you will have this relativistic suppression to the scalar interactions if you want. But because there are so many, you can compensate that, right? And then you can have some bounds. The bounds that you get from solar are around the same bounds you get from this relativistic today. This is why we didn't, I mean, we put references, but we didn't put it in the plot because it's pretty much the same thing in this strength. But yeah, solar physics is one of the physics that may be affected by that. Another thing, it's supernovas, right? We are all expecting this next supernova to explode. And now we have a lot of neutrino experiments. And if that happens, I mean, it's an environment with a lot of neutrinos and neutrino physics going on, then it should be a good laboratory for this kind of physics, probably too. Yeah. Yeah, but besides that, I don't think so. There is much.
Yeah. Other questions?
I have a question. So Jordi, can you say, you already said it, but what is the mass of the scalar again in electron volts?
The mass of the scalar is, I don't remember exactly the number. What is the mass of 1 over the astronomical unit? let me check. Maybe I put here some numbers. No, here is much. I think it has to be like 10 to the minus 19, maybe 10 to the minus 12. No, 10 to the minus 19, I remember more.
In electron volts, right?
It's very light. Yeah. It's very light. It has to be very light. I mean, if you play the same game with warm dark matter, something that is heavier, then you may probably have physical effects with much heavier masses, right? Let me see. Because 1 second, I'll show you the equations here. Yeah. You see, I mean, you want this guy to be. I mean, you want these long-range interactions to be active in a region where you have high densities. At the moment, they become non-relativistic. And if they become non-relativistic earlier in the universe, this physics may be relevant with shorter interactions if the densities are higher. But at the end, you need all these ingredients.
So I have a related question. Do you expect the relic density of this scalar field as well?
No, I mean, that's a very good question. Because it's this thing, right? I mean, this is related with this term, which is what you produced. I mean, I don't expect it because I don't want to expect it. I mean, wait, what I'm telling is that we are in a regime, we wanted to study phenomenology of this intermediate regime, right? Where scatterings are not important, or where these long-range interactions are also not important. Now, these couplings, they should be at less, let's say, than 10 to the minus 7 in the strength of this coupling. And when you put the number this level or lower, then you essentially don't have thermal production. It's very, very suppressed. You also don't have annihilation, essentially. Neutrinos don't. But that's because we do it by hand.
They become large at very large temperature, so maybe in the very early universe, they can. Did you check?
In the very early universe, I think they will. I mean, of course, they will be in principle they will be thermal, but I think they should decouple before the QCD, right, or something. They should decouple very early with these tiny couplings.
Probably, yes.
I mean, what we checked is that for couplings smaller like this, and this is something that is checked in the literature as well. I mean, it's the thermal production, even for the early universe, is very small. But of course, if you move to higher couplings, I mean, that's a consequence of this model too, right? You should have for higher enough interaction some thermal relics.
And what about production in accelerators, because you have the neutrino production in accelerators, and you could, by this vertex that you have with the scalar field, you could have a process of missing energy, no?
Exactly, that's true. That's true, and that will go like the coupling square and will be very, very tiny, I think. Yeah, not possible. This is always the same history, right? If the reason you want to go to high energies is because you have some effective theory, and then you go to get close to the cutoff and see processes at order 1. This already is a very suppressed one, right? If you have this and nothing else, these processes will be, because the coupling is very tiny, they will be be very, very small. It's the same thing that makes neglect this right part in the Boltzmann equation again.
Okay, I think we are over with the time. Well, any more questions?
Maybe I can ask another one, Jordi. So I'm sorry, I didn't follow very well the part about how this extra interaction of the neutrinos would affect the large scale structure, for example, for measuring things with Euclid, right? You were mentioning something on this impact on large scale. So is it more the growth factor or some other power spectrum or other things that you measure to constrain this?
Yeah, there is two things here. One is that we are in scales that are much smaller than cosmological scales. This M is much larger than is, meaning the interaction at large scale structure doesn't play any role, essentially. It's like it doesn't grow more or less. It's just a background effect, right? But the background effect is quite dramatic because, let me show you, I have a plot showing the effect on the power spectrum, this one. You see, this is the ratio between the power spectrum and lambda CDM with non-neutrino masses, which will be this line here. Yes. And then this is what happens if you add masses of neutrinos. This is the typical physics of masses of neutrinos, the suppression due to the contribution to the Hubble and the growth of structure. And this is what happens if you add this new physics, right? You can add this blue line, for example, it adds a neutrino of 0.3 electron volt and this coupling 10 to the 5. And it kind of compensates, right? I mean, you essentially make these neutrinos massless for longer, right?
Yes,
what you
but
see.
You would have to, I mean, you know, these are very small effects, right? A few percent. So then I don't know if you would have to have some independent measure of the neutrino masses, because otherwise you get degeneracies with the neutrino masses and these interaction parameters.
You do. That's related with this, right? I think the funny part is that you can indeed constrain both, right? Because let me see the plot here. I mean, you know, you cannot go lower than this. And at some point, I mean, neutrino, this I think it's the value that Euclid is claiming that can measure. We can put a bound somewhere here. Then Euclid can indeed constrain in this direction. Now, it's true. I mean, what you say, it's true in the sense that if you put, it's true for the negative value, right? For the negative measurement. Let me show you this a second. For this, if Euclid puts a bound compatible with 0, then all this is allowed. Even higher, right? Because cosmology, I mean, neutrinos are essentially massless in cosmology. There is no neutrino masses anymore. And that's what you say, right? That there is this degeneracy. But if an Euclid measures a mass, it really measures some suppression. That's a different history. Now there is no degeneracy so much, because the interaction, if you put more interaction, then what you do is make it massless, and it cannot be, right? And this is this picture.
And these oscillations you have in the model with interactions, I think in the previous slide, you have these oscillations in the power spectrum, quite fast oscillations in the power. No, previous slide, previous.
Yeah. This one.
This one, yeah. So do you think one would be able to measure such high oscillations in the power spectrum here in some of these models?
That I don't know.
Because this is a narrow band, so this is easier to detect, maybe.
Maybe by trying to measure that, you can indeed distinguish, right, between this new physics and neutrino masses. I mean, what we put here is the forecast of Euclid with the forecast that is available, right, that all the people use to do Euclid forecast. But maybe something more dedicated to look for these oscillations can break this degeneracy.
The thing is that whenever this curve is very smooth, it's hard to distinguish from systematics. But when you have these oscillations of the power spectrum on a narrow range of scales, right? Maybe you can see the correlation function of what does that produce.
Yeah, that's interesting.
What you can measure is a bump, right? Easily.
Yeah. You're right. Yeah, no, that's interesting. Yeah, sure. I mean, we didn't. I mean, we just played the standard Euclid forecast idea, but it's a good point.
Okay.
Thank you.
Okay, thank you, Jordi. I think we can finish now. Thank you very much.
Thank you.
Next week we will have an external colloquium, so there will be no internal seminar, but we expect to continue on February 25. Thank you. Thank you all.
Thank you very much.
Thank you.